the normal distribution. And what the normal distribution is a continuous probability distribution. Okay. So, all right, what does the normal distribution look like? Oh, here's what the normal distribution looks like. The graph of a normal distribution is bell-shaped and symmetric to the mean. Okay. The mean, median, and mode are all equal. Okay. And they are located at the center. There are some extra words here. The mean, median, and mode are equal. I copied it twice. Okay. The curve is continuous. It approaches but never touches the x-axis. And the total area under the curve is 1 or 100%. Okay. All right. So take a look at this. So if you do a histogram, right, like this. So suppose you do a histogram from 0 to whatever, okay, and you divide them into categories or classes. When you have a completely symmetric distribution like this, that becomes the normal distribution. Okay, so this is what something might look like when you only look at like 100 people, right? When you only poll 100 people. Or 1,000 people. So do you see how as you add more, it gets more like symmetric? And then 10,000 people. And then if you keep adding in classes because you polled the entire population, the curve will look like this. And here, the mean and the median are right here. Okay? Mean, median, they're all like at the center. All right? Okay, so do we remember what standard deviation was? It was a measure of how much values in a set differ from the mean, right? So if the mean on a test is 78%, how many points different are, most test values? That's the standard deviation. Remember what we talked about when we talked about the standard deviation. So standard deviation measures the variation among data values. Okay, so it tells you, are all the data values close to the mean or are they farther away from the mean? If all the test scores are close together, like if everybody got between 80 and 85, then the standard deviation is very small. So if the values are close together, there is a small standard deviation. But with more variation has a bigger standard deviation. Okay? And then, okay, so some other important things. For many data sets, we say a value is unusual if it differs from the mean by more than 2 standard deviations. Okay, so suppose everybody took a test, and suppose the average was an 80, and the standard deviation is 5, right? So 80, the mean is 80. Oops, mean is 80. And suppose standard deviation was 5. That means most of the tests are between 85 and 75. Right? Most of the scores are within 85 and 75. Now, what happens if you go 2 standard deviations above? What happens if you add 5 plus 5 and then 5 minus 5 minus 5? You get 70. Okay? So if you go 1 standard deviation, 5 minus 5, you get 85 and this. 2 standard deviations, you get this. So if the mean was 80 and somebody scored lower than 70, that's 2 standard deviations away, we say, well, that's an unusual score. Okay, because everybody scored to 80 and that one person got a 69. Okay? All right, so take a look here. The shape and position of the normal distribution depends on the mean and the standard deviation. Okay? So take a look here. If the standard deviation in a graph gets larger. Okay, so take a look here. Sigma 1, the standard deviation of the blue graph is larger than the red graph. So what happens to the peak? Then the curve is what? The curve is higher. Okay? When the mean of the data changes, the graph like shifts horizontally. Okay, so here's the big rule of this section. It's called the empirical rule, and it's called the 68, 95, 99.7 rule. All right, those numbers you just have to memorize. I'm not going to give them to you. 68, 95, 99.7. Okay. For data sets having a distribution that is bell-shaped, so if you have a normal distribution like this, the following properties apply. 68% of all values fall within one standard deviation of the mean. So take a look. This is the mean, okay? And suppose the standard deviation is this much, S. So if you go S units away and S units away in both directions, all of the scores, all of the data that falls within that region, that's 68% of all of the test scores, let's say. So if 100 people took a test, okay? And if the mean is right here, if you go one standard deviation to the left, one standard deviation to the right, 68 scores are going to be in there. Okay? 34 and 34. Does that make sense? Okay. If you go 2 standard deviations above, so here is the mean. Okay? I went 1 standard deviation. Now I go another standard deviation. Now, within this total region, you have 95% of the data. All right, and the 95% is distributed symmetrically. So 34, 34, 13 and a half, 13 and a half. Together, it's 95%. Okay, so how much is only within this part? What percent is this part? What percent is that part? Not all at once now. What? 47 and a half. Okay, now if you go 3 standard deviations, that's 99.7 of the data. So if I go 1 standard deviation, 2 standard deviations, okay, and then a 3rd standard deviation, in that region, I cover 99.7% of the data. And if anything that's like anything past 3 standard deviation, that's just an odd score. Okay? So take a look. Suppose these were the heights of a population. Suppose these were the heights of the US, like people in the US. Men, you know, in their 30s, because they've stopped growing hopefully by then, right? Men in their 30s in the US population, right? In the US. So this is the mean. Okay, that's the mean and that's the median. So, you know, that's where it is. Now, and suppose the standard deviation is like a couple of inches, right? So if you're within 1 standard deviation, like 68% of the people are within that. 95% are going to be within 2 standard deviations, and then 99.7%. And if somebody lies like over here, they're either like grotesquely tall or super, super short. Okay? All right. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. Okay? This stuff right now is where like real people in their jobs use this stuff, right? If you have a real statistician. All right, so here it says what percentage of IQ scores are between 70 and 130. All right, so here's what we do this. Here's how we do this. This is how the distribution looks. The mean is 100 and the standard deviation is 15. Okay? Now, that means here and here, if I go 15 over and 15 over, what points are those? If this is 100, if I go 15 to the right and 15 to the left, what points are those? What point is this one? 15 to the right. This was 100, 15 to the right. 115. And what's the one on the right, on the left? 85. Okay, what percent are within those? What percent is within the one standard deviation? 68. But is that what I want? What I want is 70 and 130. That means I have to go one more 15. 130 and 70. Okay, so what percent is there? That's 2 standard deviations. That means how much? It's the empirical rule, right? 95%. Right? So you're always going to go with the 68, 95, 99.7 rule. One of those numbers. Right? But like you could be asked, or it could be half or whatever. Okay, the heights of 860 students at East High School are normally distributed. Right? Normally distributed, it means they have that bell curve, right? With a mean of, so the mean is 67 inches and the standard deviation of 2.5. About how many, not what percentage, how many students are 72 inches tall, are more than 72 inches tall? So this is a little bit more intricate. This is the mean, 67. The standard deviation is 2.5, right? So if I go here, okay, now you want more than 72 inches tall. That means I'm going to look at the graph to the right, okay? So more than means look to the right. Okay, how many standard deviations do I have to go in order to hit 72? If I go one standard deviation, that's 69.5. And if I go another standard deviation, that's 72. So I went 2 standard deviations. Okay? Now, how many students are more than 72 inches tall? So, if I go here, look, okay, how much is this? How much is that? That's 95. So, how much is just this blue part? How much is just that blue part? Good, it's 2.5. Because look, if this is 95, then the little bit on the left and the little bit on the right are 5% together. That means this is just 2.5%. Okay, so 2.5% are taller. Well, that's fine, but it wants the number of students. So 2.5% of 880, 0.025 times 880, how much is that? Somebody, anybody? Do you guys have your phones, your calculators with you? So 22. So it's 22 students are 72, are taller than 72 inches. Okay, what percent of the students are between 59.5 and 69.5? So 59.5 and 69.5. All right, well, let's go lower here. If this was 67, right, and if I go 2.5 lower, that's 64.5. Oh, no, wait. Oh, yeah, sorry. So that's 64.5. And if I go lower, it'll be 62. And I have to go one more to 59.5. Right? Okay. What percent is between, I need another color now. Okay, so what percent is between 59.5 and 69.5? All right, so how much is this? 1, 2, 3. How much is this part on the right of the mean? That black part, you know what, let me draw it again, because that got confusing. Okay, so this is 67, and then whoop, boop, boop. This is 59.5. I went 3 standard deviations, and then this is 69.5. Okay, if you go 3 standard deviations, right? That's, how much is that? That's 34, 13.5, and 2.4, right? So 34, 13.5, and how much? 2.4. And then this much is 34. So it's going to be 34 plus 34 plus 13.5, 2.4. Okay? So 83.9%. Right? So here's where it can get a little tricky. Not necessarily like super difficult, but a little tricky. Does that, right? But it's all stuff you could do, right? Okay, let's do some z-scores. Okay. We call this z-score, or some people call it z-value. Z-score is more common. Okay, so remember when we said box plots were easy to like visually see what's happening? No. You just have to know, the magic rule, 68, 95, 99.7, right? But all those numbers are half. So it's 68, 95, 99.7, right? So 68, half of those are 34 and 34. That makes 68 together, right? And then, like, you go, how much is it from 68 to 95? It's 27. If you split that into 2, it's 13.5 and 13.5. Okay, and then how much is it from 95 to 99.7? It's 4.8. So you split it between 2.4 and 2.4. Honestly, we don't use that all that often. Okay? So that's what it is. If you just know these, and then the difference you split, the difference you split. All right, so a z-score helps us just like a box plot to compare data, because it's like, you know, leveling it, so you're comparing apples to apples. All right, so what is the z-score? It's also called the standardized value. It's the number of standard deviations that a given value is above or below the mean. Okay, so if a value falls here, right, that's 1 standard deviation away, it'll have a z-score of 1. You see what I mean? If it falls like here on this line, it'll have a z-score of 2. Does that make sense? Okay. So the way you calculate the z-score is this. And what is that? It's x minus x bar, the value minus the mean. So subtract from the mean. We do that all the time for the standard deviation as well, right? X minus x bar over sigma. And we always round to 2 decimal places. Okay. So here we go. X is 24, x bar is 29, and that's the sigma. We want z. So z is x minus x bar over sigma. Yeah, I was just about to say that. Don't switch the order because negative or positive makes a difference. This is 29, right? So that's negative 5 over 4.2. Oh my gosh, why can't I? And that's 1.19, negative 1.19. What does that mean? It's 1.19 standard deviations below the median. So if this is the population, if that's the distribution, that's the mean. This is 1 standard deviation. If it's negative 1.19, it's a little bit past 1 standard deviation. Okay? On the left-hand side, on the negative. Okay, so like if it's like height, somebody is a little bit shorter than the average. And now here we want x. So z is x minus x bar over sigma. We're given z, x minus x bar over 2.3. Multiply both sides by 2.3. I should. 48, my mind wandered. Okay. So multiply both sides by 2.3. And I get 979. Let's keep all the, what do you call it, values. So then we add 48. And x is negative 44. Positive, I'm sorry. Positive 44.021. Now, if x bar is given to you in whole numbers, keep it as to as many places, decimal places as x bar. Okay? So x would be 44. All right? So same decimal as x bar. Okay. All right. Consider a comparison of two individual data values as we try to determine which is more extreme. Okay. So you want to see which is more extreme. The man who is 76.2 inches tall, or a man who is 237 pounds, right? You want to see which one is more extreme, huh? No, so these are completely different things. Yeah, right. These are our individual x's. So we can't compare the values directly, right? Because it's height and weight. One is apples, one is oranges. So what you have to do is you have to compare the height to the height of the population and the weight to the weight of the population and see which one is farthest from the mean of that particular statistic. Okay, so is the height further away from the average of the people's heights, or is the weight further away from the average of all the men's weights in that population, not in a different country? So what we're going to do is we're going to compare the data values by finding their corresponding z-scores. So we're going to find the z-score of the guy's height and the z-score of the guy's weight. All right, and we have to always compare it with data. So for men, the heights have a mean of this and a standard deviation of this, and the weights have this. So let's do height first. All right, and what I'm going to do is ZH, and that's going to be x minus x bar over sigma. So ZH is going to be 76.2 minus 68.34 over 3.02. and that's 2.60. For the weight, do the same thing. Uh, 237.1 minus 172.55 over 26.33. And that has a z-score of 2.45. Well, what's more unusual now? Which one has a higher z-score? The height, right? The guy with the height of 76.2 inches. So he's much more, he's much more extremely taller than the other guy is extremely, is extreme by weight. Does that make sense? So this has a higher z-score. So the 76.2 inch man, well, he's not more unusual. His height is more unusual, right? We don't want to diss the guy. Okay, and that's just statistically speaking. Don't go tell. We want to find the middle 50% of the data, right? So that looks like this. If that's 50%, okay, then this is the, what percent mark is that? If that's 50% of the data, then around it you have 50% of the remaining data, right? So this is, the 25% mark, and this is the 75% mark, right? And in the middle of it, you have 50% remaining. So what you're going to do is this. On the calculator, you're going to do second variables or distribution, and you're going to take number 3. And here, because it's 25%, we're going to put in 0.25. Enter, 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 blah. Okay, and here we get negative 0.67. So I write that here, negative 0.67. Now, less than or equal to, z less than or equal to, and then I'm going to do it again now for the upper part, 0.75. All right, so now I do the same thing. You could do like control enter and bring the same thing back. And here, just switch it to 0.75. And I get 0.67. Okay? All right, so let's do that again. Now we want the outside 20% of the data. So that means, first of all, if it's 20%, then inside you have 80%. So here you have 80%. What you want is the outside 20%, so this and this. Okay? Now, how do I find these points? If inside is 80%, right? And outside is 20, so basically it's going to be the outside divided by 2. So 10%, 10%. Okay, so how we do these numbers is, here we wanted 50%, right? The middle 50. So you do 100 minus 50. That's 50 divided by 2. Here, right here, okay, the inside is 80. So basically you're going to do 100 minus 80 and get 20. 20 is the outside number. Divide by 2. Now, if they already gave you the outside number like here, then just divide that by 2, right? So this time, it's going to be here. 0.10, right? So that's negative 1.28. So if you want the outside, then you want your z-score to be less than or equal to negative 1.28, or you want your z-score to be greater than or equal to, and if you do it again, it's going to just give you the 90. Oh, sorry, this is 90.9. It's just going to give you the positive version of it, 1.28. Okay? All right, so with that, go ahead and continue with the homework.